In the previous video, I talked about the solution to first-order linear differential equations with constant forcing functions. In this video, we'll use those results to determine the response of first-order circuits with constant inputs. When determining the responses of first-order circuits, I typically won't explicitly solve the differential equation governing every circuit that I analyze. Instead, I'll rely on knowing the form of the general solution for the type of differential equation I'm solving. Then I just need to determine the unknown coefficients in that function. This approach results in a significant reduction in effort required to analyze a circuit, but it does require us to make sure that the circuit we're analyzing actually meets the criteria for the assumed form of the solution. In this unit, we're assuming that the circuit is a first-order linear system, which will be governed by a first-order linear differential equation. This means that the circuit can have only one independent energy storage element. The form of the solution that we'll use also relies on the input to the circuit being a constant during the time of interest. In our derivation of the form of the solution, we wrote the differential equation in standard form for the time period of interest. In this form, the multiplicative factor on the highest order derivative is 1. That makes the multiplicative factor on the 0th order derivative equal to 1 over the time constant. Since the input's constant, the right-hand side of this equation is a constant. The time period of interest will be time greater than 0. This equation can also be represented using unit step functions. The left-hand side of the equation is unchanged, but the input is written as a times u0 of t, where u0 of t is the unit step function. Thus, the input here is only non-zero for times greater than 0, and it's a constant over that period of time. When we solved this equation, we found that y of t was equal to y0 minus yf times e to the minus t over tau plus y sub f. In this equation, y0 is the initial condition, the value of y of t at time t equals 0, and yf is the final value of y of t, or y as time goes to infinity. Since the input's a constant, the final value of y of t will be a constant. Now let's determine the response of an RC circuit to a constant input. Any linear circuit containing a capacitor can be represented as a Thevenin equivalent circuit connected to that capacitor. So this is a general model for any RC circuit. The switch here closes at time t equal to 0, applying a constant voltage to the capacitor. We want to find the capacitor voltage, V sub c of t, as a function of time for times greater than 0. As we've already seen, the differential equation governing this circuit is this. We determined this equation by performing KVL around this loop and noting that the resistor and capacitor currents were the same. The initial voltage across the capacitor is V0. In order to be rigorous, the initial condition is defined at t equals 0 plus. The plus denotes a time instantaneously after the switch closes. Since this differential equation is in standard form, this term is 1 over the time constant, tau. That means that tau is equal to the capacitance times the Thevenin resistance seen by the capacitor. Since the input is a constant, the capacitor voltage as time goes to infinity must be a constant, and the derivative term in this differential equation goes to 0. The RTH times C terms cancel out, and the capacitor voltage as time goes to infinity is just VOC, the supply voltage. This is the form of the capacitor voltage response. The unknowns in this equation are the time constant, the initial voltage across the capacitor just after the switch closes, and the final voltage, VOC, across the capacitor as time goes to infinity. Next, I'll do an example to show how to calculate those three values. In this example, I have a switch that's been at position A for a long time and then moves to position B at time t equals 0. I want to find the voltage across the capacitor, V of t, for times greater than 0. First, I need to check to see what criteria the circuit satisfies. This circuit has only one energy storage element, a capacitor, so it will be governed by a first-order differential equation. The applied voltage is constant, 12 volts, for time greater than 0. Our circuit elements are all linear, so the governing differential equation will be linear. Since we have a linear first-order differential equation with constant input, the solution to the differential equation has this form. Since the energy storage element is a capacitor, the time constant of the circuit is the Thevenin resistance seen by the capacitor times the capacitance. At this point, we've converted our original difficult problem to three very simple problems. We just need to find the initial voltage across the capacitor, V0, the final voltage across the capacitor as time goes to infinity, and the circuit time constant. Keep in mind that these three problems are completely independent from one another. I can solve for the three unknowns in my equation in any order I want to. I'm going to determine the initial condition first. The initial condition is the capacitor voltage at time t equals 0 plus, just after the switch is moved to point B. To find this, I'll take advantage of the fact that the capacitor can't change its voltage instantaneously. That means that if I find the capacitor voltage just before the switch moves at time t equals 0 minus, that value will be the same as the voltage at t equals 0 plus. The circuit I'm going to analyze then has the 3-volt source connected to the capacitor. The source is a constant, so at t equals 0 minus, the capacitor voltage has become a constant and the capacitor behaves like an open circuit. That means the circuit I want to analyze looks like this. I strongly recommend redrawing the circuit under the desired circumstances, as I've done here. Redrawing the circuit keeps me from getting confused and making silly mistakes. In this circuit, since the capacitor is an open circuit, there's no current through there. These three resistors all share the same current, so they're in series. I can use a voltage divider to find V equals 0 minus then. So V at 0 minus is equal to the total voltage, which is 3 volts, times the 12 ohm resistance over the sum of the three resistances. 2 and 4 and 12 is 18 ohms. That's 2/3 of 3, so V at 0 minus is 2 volts. Since the capacitor's voltage can't change instantly, that means the voltage at t equals 0 plus, the initial condition that I want, V of 0 plus, which is just V0, is also 2 volts. The next thing I do will be to determine the time constant. Since we're finding the capacitor voltage for time greater than 0, the time constant we want is a property of the circuit for time greater than 0. For time greater than 0, the switch is in position B, and the 3-volt source and the 2 ohm resistor are disconnected from the circuit we're interested in. So this is the circuit for time greater than 0. Again, to avoid confusion, it's a good idea to redraw the circuit as it should be during the time of interest. The time constant for an RC circuit is just the Thevenin resistance seen by the capacitor times the capacitance. To determine the Thevenin resistance, kill the independent sources, so this voltage source becomes a short circuit, and determine the resistance seen across the capacitor terminals. Remember that these terminals are not an open circuit here. We're looking for a relationship between the voltage across the terminals and a current through the terminals. The capacitor terminals and the two resistors are all in parallel, so the equivalent resistance, which is the Thevenin resistance RTH, is equal to the product of the two resistances, 4 ohms times 12 ohms, over the sum of the two resistances, 4 ohms plus 12 ohms. That is equal to 3 ohms, so the time constant, tau, is equal to 3 ohms times the capacitance, which is 2 farads, which is 6 seconds. Finally, we need to determine the capacitor voltage as time goes to infinity. For time greater than 0, the 12-volt source is connected to the capacitor. Since the input is constant, the capacitor looks like an open circuit as time goes to infinity, and this is the circuit that we want to analyze. Since this is an open circuit, this current is 0, and these two resistors share the same current. They're in series. We want the voltage across one of the series resistors, and we know the total voltage. That's a perfect voltage divider. So V at infinity is the total voltage, 12 volts, times this resistance, 12 ohms, over the sum of the two resistances, 12 ohms plus 4 ohms. So V of infinity is 12 times 3/4, which is 9 volts, which is VF in our equation. Now let's put all the pieces together and determine the capacitor voltage as a function of time. This is the form of the solution. In this solution, the initial voltage, V0, is 2 volts, the time constant is 6 seconds, and the final voltage, VOC, is 9 volts. The voltage for time greater than 0 is then 2 minus 9, which is negative 7, e to the minus t over 6, plus 9. Now let's determine the response of an RL circuit to a constant input. In this case, I'll represent the circuit connected to the inductor as its Norton equivalent circuit. The switch here closes at time equal to 0, connecting the constant current source to the inductor. We want to find the inductor current, IL of t, as a function of time for all times greater than 0. This is the differential equation governing the circuit. The initial current through the inductor is I0. As with the previous RC circuit, the initial condition is defined at time t equal to 0 plus, just after the switch closes. With the differential equation in standard form, this term is 1 over the time constant tau. So tau is equal to the inductance divided by the Thevenin resistance seen by the inductor. Since the input current is constant, the inductor behaves like a short circuit as time goes to infinity. At steady state, then, the inductor's short circuit current is this source current. This can also be determined by setting the derivative term in this equation to 0, as we did with the RC circuit. The form of the inductor current response is this. The unknowns in this equation are the time constant, tau, the initial inductor current, I0, and the inductor current as time goes to infinity, which is just the inductor short circuit current. These can be determined independently by solving 3 simple problems. In this example, I have a switch that's been at position A for a long time and then moves to position B at time t equal to 0. I want to find the current through this inductor, I of t, for times greater than 0. First, I need to check to see which criteria this circuit satisfies. The circuit has only one energy storage element, so it's governed by a first-order differential equation. The applied 3 amp current for time greater than 0 is constant, and our circuit elements are all linear. That means we have a linear first-order differential equation with a constant input. So the solution to the differential equation has this form. Since the energy storage element is an inductor, the time constant is the inductance divided by the Thevenin resistance seen by the inductor. Now I just need to find the initial and the final currents and the time constant. To find the initial condition, I want this inductor current just after the switch moves to point B at time t equals 0 plus. To determine this, I'll find the inductor current just before the switch moves and then use the fact that an inductor's current can't change instantly in order to get the desired initial condition. To get the inductor current before the switch moves, I'll assume that this switch has been at position A for a long time before t equals 0. Since the voltage source it's connected to is a constant, that means that the inductor current will have become a constant, and the inductor behaves like a short circuit. This is the corresponding circuit. The inductor current can be determined from this voltage divided by 12 ohms. If I call this voltage V1, and then determine an equivalent resistance of these 2 resistors here, this voltage V1 can be determined from a voltage divider. So Req, if these 2 are in parallel, is 6 ohms times 12 ohms over 6 ohms plus 12 ohms, which is just 4 ohms. Now V1 is from a voltage divider. These 2 4 ohm resistors are in series, and I know the total voltage across them. So V1 is the total voltage, 6 volts, times this equivalent resistance, 4 ohms, over the sum of this resistance and this, which is 4 ohms plus 4 ohms. So V1 is half of 6 volts, which is 3 volts, and I at 0 minus is equal to V1 over 12 ohms, this current, which is 3 volts over 12 ohms, which is 0.25 amps. Since the inductor current can't change instantaneously, this is also the current at time t equals 0 plus, which is the initial condition that we want. So t equals 0 plus, the current is 0.25 amps. To determine the time constant for t greater than 0, we look at the circuit for t greater than 0. After time t equals to 0, the switch is at position B, the inductor is connected to the 3 amp source and is disconnected from the 6 volt source. This is the resulting circuit. The time constant for an RL circuit is the inductance, 2 henries, divided by the Thevenin resistance seen by the inductor. The Thevenin resistance is obtained by killing the independent sources so that the 3 amp current source becomes an open circuit and calculating the equivalent resistance seen across the inductor terminals. Remember that when determining an equivalent resistance, these terminals are not treated as an open circuit. We're actually looking for a rate of change of voltage across the terminals to a current through the terminals. Since the current source acts as an open circuit and does not allow any current through it, there's no current through the 4 ohm resistor, and the 6 ohm and 12 ohm resistors are in series. That means the Thevenin resistance seen by the inductor is just the sum of the 6 ohm and the 12 ohm resistances, which is 18 ohms. The time constant, tau, is then equal to 2 henries, the inductance, over 18 ohms, which is 1/9 of a second. Finally, the final condition is the inductor current as time goes to infinity. The inductor has been connected to the constant current source for a long time, so the inductor behaves like a short circuit. The inductor current can be determined from a current divider. We know the current, 3 amps, into a parallel combination, and we want to find the current in one of the resistors in the parallel combination. So I at infinity is the total current, 3 amps, times the other resistance, which is 6 ohms, over the sum of the two resistances, 6 ohms plus 12 ohms. This is 1/3 of 3 amps, so this is 1 amp is the final inductor current. The inductor current as a function of time can be determined by plugging the appropriate values into our original equation. We found that the initial current was 0.25 amps, the time constant is 1/9 of a second, and the final current is 1 amp. The resulting current for time greater than 0 is this. I0, 0.25 minus 1 is minus 0.75. E to the negative t over 1/9 is e to the negative 9t, plus the final current is 1 amp. As our circuits become more complicated, it'll become more and more important to be able to cross-check our results in order to avoid errors. In the next video, I'll talk about cross-checking results for first-order circuits.